weird hand here. Okay, so this is your wedding ring, right? Is that the finger you put it on? Yeah, I think so, right? Okay, so let's say on a hot day, okay, let's say on a certain day you're doing some work in the yard and your finger starts, blood fills in and it expands, you know. So it's kind of hard to take it off, you know. The finger has expanded. So now you want a way of taking the ring out, right? So if you warm it, is that going to help take the ring out? So imagine this is your finger, the cross section of your finger, and then you have a ring. The ring is like this. Well, you know what? This is your finger. I'm not going to shade it in, and then this is the ring. So we could do a cool problem with that too. Okay, so let's say that it's very tight. It's like you could barely take it off. So let's say their inner radius is the same. Inner radius is what's typical finger radius? Probably 0.5 centimeter. I'm just checking my finger here. Yeah, from here to here is probably a centimeter. So the radius would be 0.5 centimeter, right? So now, as the finger, let's say I warm, so let's say the initial temperature is 20, and I can't take it off. So I immerse my finger and the ring in a lukewarm water. So the temperature rises to 30 Celsius. So that's not enough to burn your finger, of course. So is that sufficient for the ring to slide off now? Which one is going to expand more, your finger or the metal? So what information would we need? The expansion coefficient of a typical finger, right? I guess, and
the area of the finger?
The material of the ring, right? So let's look it up. So what are rings made of? Gold, I guess. Let's say it's a gold ring. So the expansion coefficient of gold. Okay. Fractional expansion per degree Fahrenheit. Wait, why are they giving us two numbers?
So for this one, we're using an alpha, right? Not a beta.
You know what? For solids, I don't care, because even if you find the alpha, you can always get to the beta by multiplying it by 3. Yeah, good question. Yeah. So you know what? Let's go back to that other side. Gold.
How do we know if we're supposed to use an alpha or a beta?
Okay. We'll find out in a minute if we need the alpha or the beta. But all I need to record right now is the alpha. You know, then we'll determine if we actually need the alpha or the beta for the ring. Oh no, these are specific heats. What am I doing?
I think that other website had it.
Where was
the one,
it?
that
Where?
one.
Gold?
Yeah, it has gold there.
Where? Oh, okay. So I'll just record the alpha of gold. 14 times 10 to the minus 6. Okay, what will the finger be? Maybe bone, right? Expansion coefficient of finger. I don't know if it will give it double diffuse convection. No. Evaluation of hand and finger heat loss with heated hand. Okay, let's just put of a bone.
What if you try skin?
Yeah, but the skin is so malleable that even if your skin expands, you can squeeze it. So the bone is what determines if you can take the ring out, probably.
Yeah.
This is biological physics now. Thermal properties of human cortical bone. Okay. The technique enables accurate measurement of coefficient thermal expansion and contraction of the average values have been measured to be 27 plus or minus 3.9 for expansion and 27.2 for contraction. So let's use the expansion one. But is this the beta? Technique enables accurate the coefficient of thermal expansion.
Well, it's only 1/17
10 to the minus, oh, it's in,
millimeters.
there should be no units there, right? Because it should be just 1/Celsius.
Right.
So the idea you see is that you should be able to Google things and interact with what's happening in the real world in any realm and make sense of these numbers. So I'm worried that this says millimeters because the coefficients we're looking for should not have.
Professor, what if you just copy and paste the title, The Thermal Properties of Human Cortical Bones? Because that was published in the 90s. I think you can find something more updated.
Oh, more updated? But I don't know if those things change. I mean, human bone is human bone.
Yeah.
Unless we're evolving very rapidly.
I think we're evolving a little bit. Have you asked LeBron James?
These are actually very technical. These are actually pretty technical coefficients of primary, coefficients of animal bone, abstract. Oh, these are ones where you have to pay to actually see it because they're very technical, advanced articles.
Yeah, anything with nature is top notch, and you usually have to pay a.
Yeah, you have to pay. You have to pay. They're not going to give you data just for free. Okay, let's just for the sake of brevity, let's just use that number. Let's just say it was that. 27.5 times 10 to the minus 6, 1/Celsius. So let's say that's the alpha of the bone. 27.5 times 10 to the minus 6. Okay, so let's say that's the alpha of the bone and that's the alpha of gold. Okay, now since the finger is like cylindrical, it expands as an area, right? Remember the circle that we did yesterday? So to find the new radius of the finger, I'm going to assume, of course, that the whole thing is full of bone. So I'm just doing simplistic, that it's like a cylindrical bone. So then I'm going to say delta A is going to be 2 alpha A initial delta T. 2 times 27.5 times 10 to the minus 6 times the A initial, pi times 0.5 squared, right? Times 10 Celsius. So that gives you the change in area of the finger if you heat it up by 10 Celsius. So so that gives you 2 times 27.5 times pi times 0.5 squared times 10 to the power -5. So this one multiplies by this and makes it 10 to the -5 equals. delta A is 0.000431968, so on, so on. So I get this big long number, right? And now the final area is going to be the initial area plus the delta A. So the initial area is pi times 0.5 squared plus this number. Right, so then I take this plus pi times 0.5 squared. So I add the delta A to the original area, which is pi times 0.5 squared, and then my final area comes out 0.78583. Notice that I'm not even rounding. I'm just writing it like this, but then I'm using the original value here. Okay, then that's going to equal to pi times r final squared. So what matters to me is finding out the final radius of the finger. Right, so then divide this by pi, okay, and then square root it. Point 5001378 centimeters. So you see, it grew. The radius grew by that amount, 0.13748. Now we want to know how much the ring grew by. Now for the ring, it kind of, think about the ring. When you extend the ring, imagine cutting the ring, and it looks like this, and spreading it out, if you could cut the ring. So it looks like a rod, right? So I'm going to treat the ring's expansion as a linear expansion, right? It's not so much an area expansion, because I don't care about the thickness of the ring. It could be a big, huge, thick ring, but that's not going to help me. You know, all I need is that I want the inner radius of the ring to expand, so that, you know, so if you imagine this expanding and then closing it back out, right? So therefore, I want the ring's radius to expand. So what was I trying to say? I want the ring's radius to expand so that it's larger than this number. You see? So what I'm going to do, therefore, is treat the ring as a linear expansion. I'm going to say delta of the radius of the ring, or I could put it this way. Imagine the circumference of the ring is the length of this rod. You see what I mean? The length of the rod is the circumference of the ring. So I'm going to say delta L is equal to alpha L initial delta T. And then what's delta L? Let's see, alpha, I'm going to put the alpha of the ring, 14 times 10 to the minus 6, right? And then L initial is what? 2 pi r. Yeah, there you go. So in other words, do the 2 pi r, where r is the inner radius, which is 0.5 again. So you see, the thickness of the ring doesn't matter to me at all. So it's just 2 pi times 0.5. You see, and then delta T is 10. That's got to tell me by how much the circumference of the inner portion of the ring increases by. You see, the circumference. So I'm putting the original circumference, and I'm putting the delta T, and I'm putting the alpha of the ring. Okay, so now let's see what that gives me. 14 times 10 to the power 6 negative times 2 times pi times 0.5 times 10. Okay, so that's L 0.000398. And then L final is going to be delta L plus L initial, right? It's the same steps that you do, right? So then you just do delta L, which is this number, right? Plus the L initial is 2 pi times 0.5. So then you add to this 2 times, let's see, 2 times pi times 0.5. So L final 3.14203.247.
Is that the
Okay.
diameter that you're adding?
Excuse me?
Is that the diameter that you're adding?
This one here? Well, I'm doing the equation for the circumference of a circle. So it's 2 times pi times the radius of the circle.
What's the one in the left side?
The arrow, it's an arrow.
Oh,
saying-
it's an arrow just showing that just take this number and then add it to the 2 pi r.
Oh,
and,
gotcha.
then this is the answer that I got.
Thank you.
Yeah, so I don't have to write that down all over again. Okay, then that's equal to 2 pi r final. Okay, here comes the moment of truth. So if I divide this by 2 pi, that will tell me the inner radius of the ring. Okay, here we go. Divide by 2. Divide by pi. So make sure you do all these calculations. Let's say you come home from a party and you can't take your ring out at night. You got to do all these calculations before putting your finger in a bucket of warm water, right? Come on, someone laugh. Okay, now, oh man. No, the finger expanded more. 0.5, oh, a lot more. 0.50007. Yeah, that's a lot more. So it actually doesn't help. So maybe you should put it in ice water. Because, yeah, it expanded, but the finger expanded more too. This is, yeah, this is, imagine this is 7, where this is 13. You see?
Professor, should run up to 0.5?
Excuse me?
I'm getting 4.935.
Where? Here?
Well, yeah, we divide.
That happened to me also. Just when you put the parentheses, it works.
Oh, wait, did I do something wrong?
No, yeah, the answer is 0.5, but when you do the answer divided by 2.5, you get 4.9.
Oh, I guess it's not digits, yeah.
Yeah, if you do parentheses, you'll get it.
Yeah, that makes sense. Okay. Yeah, I mean, it's practically fine.
So am I right?
Yeah.
Oh, I'm right? Oh, okay.
Thank you.
Yeah. Well, I'm not sure if that's true because I think usually they say when you take your finger and ring, when you warm it, the ring should come off. That's kind of what I've heard usually. Let me see. Just as the heat can cause your finger to swell, a downward change in temperature can cause the blood vessels in your hand to constrict, loosening stuck rings. Try placing your hand in cold water for at least a minute or use an ice pack to cool it off. You can even put your hand in the freezer. Oh, it is true. So I guess opposite. I thought I had heard from people that you should warm it.
Well, I think what would be is that if you, so the ring, because it's metal, it'll expand and contract more easily because of temperature changes. But when you put your hands in the cold water, it shrinks the blood vessels, and the blood vessels will take longer to expand.
Oh, so there's more complex stuff going on too, right? Not just simply bone expanding.
Yeah, exactly. Yeah.
So
Yeah.
wouldn't it be that if you, whatever you put your hand in, whether it's hot water or cold water, you're either working with your finger or working with the ring, right?
Yeah. So here's the idea. If let's just say our simplistic view from our simplistic view, if we had cooled it, what would have happened? This would have contracted, since it expanded more, the finger would have contracted more, right? And then the ring would have contracted less. You get the idea? Even I'm not talking about blood vessel, all that stuff, just simply from the bone point of view. If we had cooled the finger and cooled the ring, this number would have been a number less than 0.5, maybe 0.49 something, but it would have been a smaller number than this, right? The finger would have contracted more. Now, would that help you take it off? The answer is yes, right? So by cooling, the finger contracts more, the ring contracts, but it contracts less, right? So that means it is good to cool it from just point of view of a bone. But on the website, it's also saying that it's good to cool it because it cools the blood vessels and narrows constricts the constriction of the veins, you know. So in both ways, it's true that it's better to cool it.